If you recall, yesterday we were in the middle of this problem when we were so rudely interrupted by the end of class. So we ended up with a little bit of a cliffhanger. Our problem was to find the flow of this vector field, or this velocity field, starting at the point -1, 2 at time t is equal to 0. So when we look at the 1i plus xj, those are going to be the derivatives of x and y with respect to t. So the derivative of x with respect to t is 1. And so we just found an antiderivative t plus some constant of integration, which would be x at time t is equal to 0, which was -1. Then when we look over at y prime, we see that y prime is equal to x. So we don't want to integrate and get a 1/2 x squared because we don't want, this is not y prime of x, it's y prime of t. So we can look over to the side and we see that x is equal to t plus x naught, and we can just put that into our y prime. So I'm going to write y prime as t plus whatever we started with in the x. Now we can write down y of t, and that'll be a 1/2 t squared plus x naught times t plus whatever y is when t is equal to 0. And in this case, we know x naught, I guess I could have started with t minus 1, but here we are. We have x naught being multiplied by the t, and y naught is y when t is equal to 0. And we have those values. So our y of t is going to be a 1/2 t squared minus t plus 2. So just like we suspected, we have a parabola. X is t minus 1 and y is 1/2 t squared minus t plus 2. This is a parameterization of the parabola. If we want y as a function of x, since we know we're getting a parabola, we know that our curve is going to be our curve will be of such a form we can write y as a function of x. We can just solve the x for t. So if x is equal to t minus 1, that means t is equal to x plus 1. And I can put that into y to write y as a function of x. And we knew that was going to happen because t minus 1 is just going to, over here in the y, is just going to shift everything. X and t are changing at the same rate. They're just shifts of each other, 1 unit, left or right, depending on which one you start with. So here is the parabola where we have y as a function of x. We have the parameterized, which is super spread out for reasons. But looking at the vector field, we saw that we were going to be getting parabolas. Or at least we suspected that we were going to get parabolas. So some ways to extend practice with this. Think about this velocity field and think, what is it that made parabolas? We had a constant in the x direction, and we moved with according to x in the y direction. So what if I switch things around? What if my velocity field was y times I plus 1 times j? Think about what this velocity field looks like. Think about how this would affect the parabolas. What if I changed my velocity field to x times I plus 1 times j? What if we changed our velocity field to, let's see, what haven't I done? 1 times I plus y times j. I just rattled off 3 more vector fields. Let's label them. We don't want to go through all of them, but we should certainly take a couple of these and think about what they might look like. So the first one, I just switched everything around. Instead of one in the x direction and x in the y direction, I have now y in the x direction and 1 in the y direction. So at the point, let's say, let's see, vector field v1. So at the point 0, 0, y is equal to 0. So we go nowhere in the x direction, and the j direction is equal to 1. And just like yesterday, everywhere y is equal to 0, the vectors in the vector field will point in vertical direction. So just a 90-degree turn of yesterday's problem. If we look at the point x is 0, y is equal to 1, now my vector field is going to go 1 in the x direction and 1 in the y direction. So now we'll suspect that we're going to get a parabola going the other direction. If we look at the point x is 0, y is 2, when x is 0 and y is 2, then we go, the vector field says go 2 in the x direction and 1 in the y direction, because it's always 1 in the y direction. At the point 1, 1, x is not involved in the vector field v1. So at the point 1, 1, we go 1 in the x and 1 in the y, because it's always 1 in the y. Then at the point 1, 2, the y coordinate of the point determines the x component of the vector. So we go 2 in the x and 1 in the y direction. So we start to get the same vector field, just turned 90 degrees. If we go into the negatives, at the point x is 0, y is -1, then we have -1 in the x direction and +1 in the y, because it's always +1 in the y. So it looks like we're going to get parabolas where x is y squared. So just looking at the vector field, thinking about the flow, this looks like an x squared, x equals y squared style parabola. Any questions? Great. So the flow of a vector field is just what the vector field is going to is paths that are given by the vector field. These are going to be paths that are defined by the vector field. The flow of a vector field is a path that's going to be determined by the vector field. We're just letting the vector field do its thing. And if you drop a leaf onto this pond at a particular point, the flow is going to be the path that the leaf follows. I was trying to balance out my picture. Now I threw off the balance over here. All right, it's just going to have to be unbalanced. So the flow of the vector field is a path determined by the field. This is a leaf floating on a pond. Here's the water in the pond. For some reason, it's going in some parabola. If I drop a leaf at the point -1, 2, looks like it's going to continue on this parabola path, this parabolic path. If I drop a leaf over here, let's say at -3, it looks like it's going to drop down and then come back up. And we can find the specific parabola by, in this case, we have y is equal to t plus y naught. And then we would take the y and plug that into the x and integrate. So that's where the x is going to be the t squared. So here is a type of object. All we're doing is describing vector fields. I guess we did use a little bit of calculus when we had to integrate to find out what our path is going to be. That's determined by the vector field. But we've got this object called vector fields. And then just before this, we were talking about parameterized curves. So now we have to put those two things together. And so that's going to bring us into our first real big topic for vector calculus, line integrals. So parameterized curves plus vector fields is equal to line integrals. So when we talk about the flow of a vector field, we're imagining a leaf on the surface of the water, just being carried by the water. So we're just thinking about a leaf on the wind or a leaf on the water. We're going to combine now our vector fields, just a leaf on the wind, with a parameterized curve. So we're going to have a curve running through the vector field. So now instead of just a leaf on the wind, we're going to have a bird flying through the wind on its parameterized curve. That'll be a path. So we're going to put a curve into our vector field. So C is going to be some curve running through the vector field. Now, when we parameterize curves, we know they have an orientation, they have a direction that they're headed. So I'm going to say that my curve is going in this direction. Where the flow of a vector field, we just try to think about a leaf on the wind, just letting the wind take it where it wants to go. The curve is going to be like a bird flying through the wind. The bird has places it wants to go, and sometimes the wind will be helping it, and sometimes the wind will be hindering it. So the curve is going to be more like a bird flying through the wind. The bird has determined it wants to go somewhere, and it's going to follow some path. And the vector field will sometimes be helping the bird and sometimes hindering the bird. So if we imagine all these vectors from the vector field as being the wind, as the bird is in this early part of the path, since the wind is pushing generally up, the wind is helping the bird fly up. But since the wind is pushing negative in the x direction, it's pushing against the bird. But as soon as the bird gets past the x-axis, now the wind is blowing in the positive x direction. So now we can think of the wind as helping the bird along its path. I didn't draw the dip down here where it dips towards the x-axis a little bit, but in that little dip, the wind is now pushing against the bird as the bird tries to fly down into the wind. So the bird's like, oh, no, that's too difficult. I'm just going to go with the wind up this way. Meanwhile, if we started a leaf at the same spot, it would just follow the wind. It would push away and then push away, turn around when it gets to the x-axis, and then go back up. The leaf is following the flow of the vector field. The bird is flying through the vector field. Sometimes the vector field is helping, and sometimes the vector field is hindering. Any questions? This is the thinking that we're going to apply when we think about vector fields and a parameterized curve sitting in that vector field. We got to think about what we can calculate. So the vector field is a bunch of vectors at every point. The curve is a selection of points. So remember that a vector field puts a vector at every point. A parameterized curve is just a collection of points. So the parameterized curve is just a collection of points. The vector field is a vector at every point. So we're going to be doing something with all the vectors along the curve. Remember what integration does. We just add up a bunch of values of the function. And we have to be able to tell the integral what values to plug into the function. So we're going to be doing something with all these vectors. The vectors are everywhere, but when we define a curve that's running through the vector field, we're picking out a bunch of points and thinking about what are the vectors what's going on with these vectors along this curve. The curve has some direction to it. And because this is calculus class and we like to simplify our problem before we complicate our problem, we're going to imagine the curve as a bunch of line segments. We're going to imagine the curve as a bunch of little vectors, little direction vectors following along the curve. So we're going to evolve our collection of points into a collection of vectors. Now at every point along the curve, I've got a vector for the curve, and I've got a vector from the vector field. So if we imagine this curve as just a bunch of direction vectors, imagine that curve as just a collection of direction vectors. At every point on that curve, we've got a vector indicating a direction of the curve and a vector from the vector field. So at every point on the curve, we got two vectors. At every point along the curve, we have two vectors, a direction from the curve and a vector from the vector field. So now we just have to figure out what to do with these two vectors. Fortunately for our heroes, we have a limited list of things that we could do with the pair of vectors. I did kind of give things away, modern movie trailer style, just like explain everything in the trailer. we got to think about, I said, so just based on the fact that I said, I'm taking parameterized curves and these vector fields, and we're going to make line integrals by combining these two things. So let's kind of metagame the situation. I have parameterized curves, which we're going to think of as a bunch of vectors at all these points. And the vector field is also assigning a vector to all these different points. So I got these two vectors, and I want to combine them into something that instructors call an integral. Then we think about what integrals do. Way back to the beginning. Integrals just tell us the area under a curve. Integrals are just telling us area. So integral is just length times width. It's a multiplication, but one of the factors is variable. And so now I've got these two vectors and I want to multiply them, but they're always changing. So all we have to do now is think about how we multiply vectors, and we're down to two choices: dot product, cross product. This is just the beginning, so we're probably going to start with the easier one. So we're probably going to be doing a dot product. Any questions? How's everybody okay? All right. I don't know if everybody's just in stunned silence because I'm talking crazy, or if everybody's just like in bored silence because you're like, oh, dude, we totally saw where this is going. As soon as you said integrals, we knew that you were going to be multiplying stuff. And as soon as vectors walked into the picture, we thought you're going to be dot producting a bunch of stuff. And then for some reason, adding up all those scalars. And yeah, that's pretty much what we're doing. We're fine. Now remember that the dot product is a scalar product. So we're going to combine at each point along the curve. We're going to take the direction vector from the curve and the vector from the vector field, find their dot product, and that's going to drop out a scalar. And then we're going to add up all those scalars. This raises a question. What is this line integral going to represent? But just like on Legal Eagle, the answer is always, it depends. What does your vector field represent? What are the points on the curve? What do they represent? What does the dot product represent? So trying to figure out what the line integral represents is just a problem of what the dot product represents. So when we're trying to figure out what line integrals represent, we just need to figure out what dot products represent. In the same way, when we were looking at integrals, instead of looking at the problem, here's an application of this integral, think about what the integral is trying to do. The integral is just taking f of x times delta x and multiplying those two quantities, length times width. If length is in meters and width is in meters, then the integral is going to be length times width, meters squared. If your function was a rate in meters per second and your width was time in seconds, then meters per second times second is meters. Apparently, the integral is going to tell you some kind of distance or displacement. If one of your factors is force in newtons and the other factor is distance in meters, then your integral is going to be in Newton meters or joules. If one of your factors is area and the other factor is length, then your integral is going to tell you area times length, meters squared times meters, or meters cubed, volume. So what the line integral can represent is anything that a dot product can represent. So thinking about what line integrals represents boils down to thinking about what dot products represent. Because all we're doing is figuring out a bunch of vectors at every point, figuring out a bunch of a collection of those points and assigning another set of vectors to those points and finding the dot products and then adding them all up. Because that's the other thing integrals do. They just add stuff up. Riemann sum and all. So when inevitably the question comes up, who does this? What is this stuff? What's this stuff for? That question just goes right back to what's a dot product for? So think about all the things that we can use the dot product for. And then we'll see if it fits into this context of line integrals. Any questions? As usual, I'm going to rely on this flow with a leaf on the wind and the parameterized curve, a bird flying through the wind. Because we can see that at each point the bird has to do some, exert some force to fly, and maybe the wind is doing some force against it. So we can calculate the work that the bird has to do to fly this path through the wind. Maybe that's one of the interpretations that we can have. Any questions? So this is what I want you to think about when you're out and about after class today. I want you to imagine there's a vector field flying through, just flowing through the room, just the air flowing through the room in all its different directions. And then I want you to imagine, well, a bird in the house would be, that would be unlucky. So just imagine a fly flying some parameterized curve through the house. Sometimes the air in the room is pushing against the fly. Sometimes the air in the room is pushing with the fly. So instead of a bird flying through the wind, if you're indoors, imagine a fly flying through the wind. I don't know if it's called wind if it's in the house. You know what I mean? You know what? Go outside. I can see that it's sunny out in my area, so go outside, look for a bird flying through the wind. All right. That's a lot to think about. I want you to go outside and picture the bird flying through the wind. It's also just nice to get outside. That's going to do it for today. I'll see you all on tomorrow. We'll talk more about line integrals. Everybody have a good day, and thanks for playing.